If you can hear me, can you just give me like a thumbs up or something? Okay. All right. Today will be the first class in the Cairo Security Bootcamp 102, and I'll be taking us through like the Starknet architecture because I believe as security researchers need to first of all understand how the architecture of what you want to carry out audits on look like, or basically properly understand it. And so in today's class we're going to be walking through the Starknet architecture, and yeah. So I'll just share my screen and we can get started. Okay. Yeah. Can you see my screen? All right. So, um, yeah. So just um, a brief about me, right? So the name is Darlington. I work as the ecosystem associate agent, and you can always reach out to me on Twitter at Xerex Darlington or on Telegram at Darlington68. And so, as regards to the agenda, or basically like a curriculum of what we're going to be looking at today. So, first of all, we're going to be looking at the network topology on Starknet. We're going to be taking a look at the transaction lifecycle. We're going to be taking a look at how proving works on Starknet. We're going to be taking a look at the data availability problem. And finally, we're going to be taking a look at how Starknet achieves L1 to L2 communication. It's going to be, I'm going to try to break things down to as basic as I can, right? So let's just try to follow picking attention and follow, since we don't have a lot of time at our hands. Yes, so starting from the network topology, uh I remember when we first talked about the bootcamp, right? David said the bootcamp was going to be for people who had already started programming on Starknet with Cairo. So basically, you had one of the requirements to partake in the bootcamp, right? Was you already had prior Cairo knowledge. So, but by any chance, is there probably anybody in the call um who hasn't written Cairo previously, or it's your first time hearing about Starknet? Is there anybody like that in the call? Maybe you could just use an emoji, thumbs up, anything at all. Okay. There's nobody. Okay, so means we can move at a faster pace. All right. So the first thing we're going to be looking at, with regards to Starknet's network topology, right, is the sequencer. Now, the sequencer is a concept you're probably already familiar with, right? It's the entity in charge of accepting, aggregating transactions, processing transactions, and basically producing blocks. So, you would probably want to think of the sequencer as something similar to like validators in Ethereum, although probably the current difference probably be that currently the sequencer is centralized in Starknet, while um basically the concept of validators on Ethereum is decentralized, right? And one key requirement for sequencer is it has to have high liveness, right? Because like I said, sequencer is um the man, or the entity, rights, which is responsible for collecting transactions, aggregating them, processing them, and then putting them in a block. Then we have like the prover, which is the entity in charge of receiving blocks. So when the sequencer has probably received transactions and probably have put them in the block, right? It's passed on to the prover, who is responsible for like processing the blocks and generating a proof of their correct processing from it. So the prover is also responsible for sending these proofs right to like Ethereum, where it is like stored in the facts registry. So the basic requirements for the prover, right, is basically a it has high machine requirements, right? You need like a lot of processing power, but then you can basically split it into smaller proofs, and this can basically be done asynchronously. Then the third entity or the third important participant in Starknet's network topology, right, are nodes. So nodes are concepts which we are probably already very much familiar with from Ethereum. So these entities are responsible for like keeping track of the latest state of Starknet, right? So there are different kind of nodes. There are different ways they can actually do this. So one way is by replaying every transaction, but this particular type of node requires like a very high hardware requirement. Another way is like relying on L2 consensus, which has a con of trust assumptions because you're basically trusting the L2 consensus. And we have the other means, which is by checking the what's it called, the proof validations on layer one. So there are a lot of nodes currently on Starknet. There's Pathfinder, which I think was one of the first. There's the Juno node by Nethermind. Um there's which one am I forgetting? But there are a lot of full nodes on Starknet. You could probably check them out later in Starknet documentation. So the second section we're going to be looking at is like transaction lifecycle. In here, we're going to look at the states which your transaction passes before it gets accepted on the Ethereum layer one. So the first step basically is preparing the transaction. So this is what's probably done behind the scenes when, let's say, you go on it up, you try to interact with it, and basically sign a transaction with your agent, your Bravos wallet, and then send it to the sequencer. So basically, you query for the nonce, you sign the transaction, and then you pass the signed transaction to the sequencer. Now, when the transaction is passed to the sequencer, at that point, the state is marked as not received. So the next thing that happens is it's basically queued at the sequencer. So in here, the sequencer acts like kind of like what we like the mempool on Ethereum, right? So transactions are queued and processed in a first in, first out order. So basically, when your transaction gets processed by the sequencer, right, it moves from a state of not received to received. So please give me a minute. Yeah, sorry about that. Um, so as I was saying, right, so in here the sequencer acts like the mempool on Ethereum. Transactions are passed on to the sequencer, they get queued and they are like processed in a first in first out manner. Now we have different states on Starknet, right, which you can probably track from block explorers like StackScan and Voyager. I particularly like how StackScan does it, right? So you can basically track every state of your transaction. So it states that you've probably like you are probably familiar with, right, is dependent state. Now this happens when your transaction has been picked up by the sequencer and executed, right? So at this point the transaction has been executed, but the state hasn't been effected already. So the basically the transaction at this point, like I said, has been executed, so events has been emitted, and all right, but it does not have a block number yet, as it's yet to be put in a block. So at this point, the transaction is marked as pending. Now, remember, when you just send the transaction initially, it is marked as not received. When the sequencer receives the transaction, it's marked as received. That's the sequencer is trying to tell you, okay, I'm now aware of your transaction, right? Now, when the sequencer now picks it up from like let's say the mempool or the gateway and executes it, it changes from received to pending. Now, the other state which we're probably very familiar with, right, is the accepted on L2. So at this point, the sequencer has picked up a transaction, added it to a block. So now your transaction has like a block number attributed to it, right? And now at this other point, no proof is generated, but your transaction has been executed and can be said to be secured by like the layer 2 consensus. So now it moves from the state of pending to like accepted on L2. Yeah. So from version 0.12.1 of the Starknet sequencer, right? So pending now is the same as accepted on L2. So pending basically is the equivalent of the sequencer saying, yeah, I've executed a transaction, I know it's valid, and I'm soon going to put it in a block, right? So we could actually say it offers the same level of guarantee as accepted on L2. And that's the reason why, if you notice, the pending state now appears as accepted on L2. So automatically, when your transaction is like executed by like the sequencer, stacks can voyage and all the market automatically as like accepted on L2. Then the final state is like the accepted on L1. At this point, the prover has picked up the blocks and has generated like a proof of validity for it. So these proofs that have been generated will now be sent to Ethereum, where it is like validated by the verifier contract on Starknet on Ethereum. That's Starknet's verifier contract on Ethereum. So at this point, we can now say, okay, these blocks are now secured by Ethereum's consensus. And that's when we now move from accepted on L2 to accepted on L1. Probably you've always noticed, right? The transition from accepted on L2 to accepted on L1 usually takes the longest time because most times the prover has to like batch a lot of blocks together before a proof is generated and like sent over to Ethereum just to like reduce costs. So just before Cairo 1 came in, right, for those of us who are like familiar with Cairo 0, so if you came into the space earlier when Cairo 0 was still a thing, you would know that Cairo 0 had one major shortcoming, and that was the fact that you couldn't generate a proof for a failed execution. So it meant that if a transaction failed, uh, the sequencer basically could not charge for that particular transaction. And yeah, so failed transactions were treated like invalid transactions on Ethereum. They were automatically marked as rejected. So, but with the move from Cairo 0 to Cairo 1 and the introduction of the intermediate layer Sierra, right? Now the sequencer can basically generate proofs for failed transaction and thus charge fees for them because like I said earlier, the inability to like charge for failing transaction made Starknet prone to like a DOS attack, right? So, but from 0.12.1 going up, the sequencer can now charge for failed transaction. But by 0.13.1, right, a new feature was added to the prover, which enabled it to be able to prove invalid transactions. So right now, proofs can now be generated for invalid transactions. Example, invalid transactions are like transactions which fails like let's say which fails a particular assert statement or whatever, right? So now proofs can now be generated from for them. So a summary of your transaction life cycle, right? So we have different statuses. The first status, like we went over, is still not received. So at the not received status, the transaction is not yet known to the sequencer, right? The receive status, the transaction has been received by the sequencer and can either be executed successfully or rejected. Then we have the pending states, which is the point at which this transaction successfully enters like a pending block. We have the rejected states, which happens when the transaction is executed unsuccessfully or was skipped, right? Then we have the accepted on L2 state, which which a transaction has when it has been successfully validated and has entered like a created L2 block. Then finally we have the accepted on L1, which is the state a transaction has when its proof has like been accepted on chain. Then the next section we're going to move into is like the proving, understanding how like Starknet proofs are generated and all. But before that, I was wondering, we have questions. David, is there like a format for the bootcamp? Can participants ask questions within as the section is going on, or do we have to wait till like the end of the bootcamp? Sorry, till the end.
So yeah, so we could do it. Maybe you just take a break. They take questions and then you move up, right? I think that makes more sense. So as they don't, we don't just cut you when you're talking. So maybe you take a break and then they ask questions due to from like the ones what you have actually explained. So I think this is also a good time for them to ask questions before you move forward.
Oh, okay. So I don't know. Does anybody have any questions?
So you could just raise up your hand, I call on you, and then yeah, you could shoot out your questions. Okay, so I want to believe. Okay, so we have Kazim.
Yeah, yeah, Kazim, you can please ask a question.
Okay. You were talking about before moving to the proving. You talked about the sequencer. You talked about the prover. Um, my question is the prover we have in Starknet, is it just one or there are a lot of prover? And if it is just one, what happens if the one like if it stops working, maybe like due to some unforeseen circumstances? What happens at that moment?
Okay. Yeah. So I guess you actually are referring. The prover is just. I believe the prover is just one currently, which is like Sharp, which is operated by Starknet, same as the sequencer. The sequencer is also currently not what we call decentralized, although it's in Starknet's roadmap to ensure going at some point, right? The Starknet sequencer will be like totally decentralized, right? So, but just like you said, right, the disadvantage of the sequencer being centralized, yeah, if for some reasons the sequencer goes down, it means during that particular period there's probably not going to be any block being created or proven or anything basically. So, but yeah, they're working towards decentralizing the sequencer.
Okay, okay. Thank you.
Yeah, I don't know if you have any questions before we move on. Okay, so in the absence of questions, I guess we can just move on. Um, yeah, so in this section, we're going to be looking at how stack proofs are created and sent to Ethereum. So probably have different questions. How do you generate a circuit for your Starknet program or carry program? Do you need to write a verifier contract? How you send proofs to Ethereum? Well, you do not need to generate a circuit for your Starknet Cairo program. You do not need to write a verifier contract. You do not need to manually send proofs to Ethereum. this is where Cairo excels above similar, should I say, DSLs or programming languages, right? Because I think my first encounter with zero knowledge proofs was Secom, and most times, probably like when we were working with Secom, you had to write circuits, and when you write the circuits, probably you had to generate proofs for them, which was going to be passed on to like Ethereum verifier contract and all those, right? But with Cairo, all these things are like abstracted behind the scenes, right? So Cairo basically stands for CPU air. Horrible naming, I know, but like basically stands for CPU air, and it's basically the only circuits you need to write. It's the only thing you need, right? So you write your codes or write your logic in Cairo, and every other thing is handled for you behind the scenes. So basically, Cairo has a verifier which is already written and deployed, which is written, deployed, and like audited on Ethereum, which is the verifier smart contract we talked about. And the Cairo language basically compiles your written logic to instructions that are executable by this CPU. Correct execution of like your program generates a proof which is understandable by the verifier. And those you have like one circuit, you have one circuit that can basically adjust to multiple logics. So Starknet basically is a Cairo program. So when you probably start learning Cairo, um the first thing you are probably thought is that a Starknet contract is different from a career program, although a Starknet contract is a career program. But contracts probably when you start writing contracts, you have to start with like um the contracts attributes and a whole lot of other things, right? So a career program, a Starknet contract is a career program, and basically deploying and executing a smart contract on Starknet is proven as part of a bigger workload. So you can see this illustration that was used here. You have like the sharp prover, you have the Starknet, and you have your smart contract, which you're going to like explain in details. So this is like your logic, which is written in like Cairo and sent to Starknet, and basically all the logic you write and all right is proven as part of like a bigger Starknet workload, which is basically sent to like the sharp prover. So now what exactly is like the sharp prover, right? So the sharp stands for shared prover. I just realized saying sharp prover is probably like tautology because yeah, more or less saying like shared prover. So but sharp stands for shared prover, and it's responsible for aggregating Cairo jobs, and thus allows diminishing the marginal cost of verification for a job. Now let me try to break this down in simpler sentence. So think of Sharp as like should I say a boss, right? And you probably know that, right? What's it called? Verifying these proofs, these generated proofs on Ethereum is expensive and like cost a lot of money. I think even counters to about 98% of like your the cost for executing like Starknet transactions, right? So we know that okay, verifying these proofs is like super expensive, right? So what Sharp does basically is it takes in a lot of Cairo job, right? It takes a lot of Cairo jobs and he aggregates them or basically combines them together and then sends them to generate a single proof for all traces, and then sends it to Ethereum to like be verified on the verifier smart contract. Now these jobs we talk about can include Starknet blocks. It can basically Starknet blocks are basically what contains in transactions, right, which was processed by the sequencer. So jobs can include your Starknet blocks. It can include workloads from StackX. So StackX is like um a different products by Stackway, and it can also include arbitrary Cairo programs. Now, we have what we call a facts registry, which is on Ethereum. And basically, when Sharp creates a proof, it creates a proof for what we would call a tuple, right? So the tuple consists of your input, which is the state of your, which basically is the state of Starknet before like a transaction, the Cairo program hash, and basically the output that's the state of Starknet after your transaction is completed. Now, this proof is basically sent to Ethereum, and it's the job or the responsibility of the verifier contract on Ethereum to like receive these tuples and the associated proofs and verify them. So basically, if the verifier smart contract checks it and okay, the proofs are valid, right? The tuples are saved on Ethereum in what we call a fact registry. So Ethereum knows that something was executed, but remember we do not pass like the whole transaction information to Ethereum. So it just knows that okay, something was executed right and it was done rightly. Now we have the Starknet operating system, which is basically like set of smart contracts that queries the facts registry for the tuple, and if the fact is there and was generated right, so we know that the proof was validated, and thus the Starknet operating system is now responsible for handling like the transition of Starknet states. So basically, it checks serious stuffs in the fact registry and updates the latest state of Starknet. So in summary, uh, when we talk about how proving uncertainty happens, right, we can summarize it in these few sentences. First of all, is smart contract execution. Your logic is included in a Starknet job. This Starknet job is further included in a Sharp job. And Sharp jobs are proving off chain. So Sharp is off chain, of course, and basically generates proofs of all the Cairo jobs that are included, right? And passes it on to the verifier smart contract on Ethereum to be verified. So verification generates facts on chain that can be by um, um, smart contracts. So the state of Starknet is those managed by a smart contract on Ethereum. So the fourth section we're probably going to be looking at is data availability. So when it comes to rollups, data availability is, should I say, a very important factor that needs to be considered, because imagine if for some reasons the state of Starknet probably after like a transaction was executed can no longer be retrieved. It means that the chain will most likely be brought to a halt, right? It can no longer move forward, and that's the reason why data, like finding a way to store and manage this data in a cost-effective way, is like super important. So define the problem, right? So we know that like I explained earlier, the Starknet operating system smart contracts queries the facts registry for like the tuple, which is the inputs, the Starknet program hash, and the outputs. So into what are the inputs and outputs in simple terms? So the inputs basically is, let's say, the state at block N, that's the state at that particular point before your transaction is executed, and the output is the state at block n plus 1. That's the state after your transaction is executed. But then the state is big, like the whole state. Like even if you try to store the state on Ethereum, right, we know that it's big and it's like super expensive. So how can we mitigate this huge cost of storing the states? So how about we store the hash instead? Now this hash is what we call basically like the state root. So just like I explained earlier, the problem is now we have like the state root at block n, we have the state root at block n plus 1. So, but what happens if for some reasons, right, the state at block n plus 1 is lost, right? Like I said, nobody can move Starknet forward. and a single entity becomes like the only validator. So the question is like, how can we solve this problem? Now, there are like three approaches to solving this problem. The first we know, of course, is the validity rollups. Then we have Validium, and we have Volition, which is the route Starknet plans to take. So validity rollups is what we are basically used to, right? So basically the go-to way for um, ZK rollups and stuff. So in this case, we are depending on Ethereum. So we publish our states on Ethereum. Uh, Hello, can you guys still hear me?
Yes, we can hear you.
Okay. I don't know. I was saying connecting, so sorry. I just wanted to confirm that. Right. So let's just continue. Okay, so as I was saying, right, so validity rollups is what we're basically used to, where these are published on Ethereum, right? So we don't exactly publish the whole state each time, but we publish like the state difference. But this in itself is still like pretty much very expensive. Like I said earlier, it accounts for about 98% of the transaction costs on Starknet. And so due to that, we probably need to think of like let's say more effective ways of like storing data. Of course, with the introduction of AI before 844, because I know someone's probably going to ask. As you can see, storing state diffs is now much more cheaper, right? So probably going to explain how AI before 844 does this in simpler terms in the next coming slides, right? But there was this talk that was held in I think in one of the Starknet CCs, right? And that was the fact that one thing we know for sure, right, is yeah, before 844 is like a shared resource, and just like every shared resource, at some point there's going to be a likelihood that we have a lot of roll-ups, probably dragging for blob space, and prices of blobs are probably are going to start like going up, and things are going to start getting more costly again, right? So question is, how can we like solve this data availability problem in in a more permanent way? And so for that, the one of the currently popular options, right, is what we call validiums, and this has to do with like storing data off chain. So basically, we publish the state routes, and we build something off chain to make sure that data is always available. Example is like Celestia. So we are probably very familiar with Celestia, right? So you can use stuff like Celestia to keep your data off chain while you publish the state routes on chain. It's pretty much safe, and but can actually become a bit expensive. So the solution, which is currently being explored on Starknet, and which would probably be the go-to. Apologies for the background noise. Apologies for the background noise. Um, yeah. So the um current approach, which is basically being explored on Starknet, is volition, right? So volition is more or less like a combination of the two, both off-chain and on-chain. So basically with volition, we publish two state routes, one for states that has to be published to L1, another for, oh my God. Sorry about that, but once again, I'm at home and things are not very organized. Yeah, so volition basically, like I said, combines the two approaches. So with volition, right, we tend to publish two state routes, one for states that has to be published to L1, and another for like states that can be published off chain, and then we let developers decide which states they want to store variables in. So this is one of like the changes emancipating most on Starknet, since I consider it a very interesting change. So more or less the idea behind it, right, is we have uh, probably when developing an application, right, you have certain states which, if lost, would be very critical to your application. So those kind of states, right, you can decide, okay, to publish them on chain. And we have those states too, which are probably, if lost, would not be very much critical to like your application. You can decide, okay, we're going to publish or push this states or these variables right off chain, and those developers can juggle between off chain and on chain, and this can help them like minimize fees that the adapts like basically consumes. So we talked about EIP 4844 earlier, which was a recent upgrade on Ethereum that makes data publication a lot cheaper. So in very simple terms, what EIP 4844 does is data is rather kept temporarily than permanently. So more or less like data are put in blob and published to Ethereum, and these blobs are like kept for like a week, then deleted. Now this helps like reduces gas fees on it, makes it a lot cheaper, right? And as you can see, when it was activated, right, which happened like I think a few months ago, right, it made gas fees on Starknet a lot more cheaper. Now gas fees are like in cents rather than how expensive it used to previously be. So, in summary, right, data availability is very important as it affects network resiliency and decentralization. Um, Validity rule of mode relies on L1 to like publish data. Validator mode relies on off-chain mechanisms. Meanwhile, volition, which is like the solutions that makes exploring, combines both. Yeah, and finally, believe that yeah, before it topo, which lowers the cost for on-chain transaction. Sorry about that once again. Yeah, so the next section we're going to look into is L1 to L2 messaging on Starknet, and basically how it works. So as we all know, right, bridging is something that's actually very important. Guys, I sincerely apologize. This will happen in the next class, hopefully. Just go somewhere quiet. Yeah, so we were going to look into L1 to L2 messaging, right? And as I was saying, right, bridging is something that we've come to recognize as very important in the ecosystem. Christian communication is also way more important, right? But as you can see, building sustainable bridges is actually super hard, and proof of this is like the numerous hacks that have happened in the previous years, right? So we know a lot of popular bridges such as Wormhole, Connect, and a lot more, right? So as I was saying, bridging is very important. And most times when we mention bridging, right, we tend to associate it with bridging assets, bridging ARC20 tokens, bridging NFTs, etc. So, but can we build more bridges? How about we go beyond bridging tokens to bridging permissions, being able to bridge computations, being able to bridge instructions, basically being able to pass logic information, etc., from one chain to another. This is what like Starknet's bridge L1 to L2 messaging basically entails. So with Starknet L1 to L2 messaging, like I said, we can build way more efficient bridges, right? Bridges that let users pass data instead of assets. And those developers can build upon this bridge, right? To build their own bridges with custom logic. We're probably going to understand how this works as we move further. So the question is why? Why is this very cool? Now think about the idea of blockchains talking natively. Now, probably before Starknet, most bridges you probably had, right? Rhino and the rest, right? Retro bridges and the rest, they are more or less about bridging assets. So you're moving ERS-20 tokens, you're moving Ethereum, you're moving NFTs from, let's say, one chain to another, right? So, but with Starknet L1 to L2 messaging, there's no element of trust involved in the mechanism. With most bridges, right? Most bridges basically, in my opinion, act as should I say centralized multi-sigs, because more or less there's always going to be that element of trust involved. You have to trust that, okay, you basically have to trust the bridging mechanism you're using, right? Secondly, with Starknet L1 to L2 messaging, right, you have a certainty of Ethereum has a certainty of what happens on Starknet, and basically mathematical proofs are generated to show that okay, message was sent to Ethereum and start and back to Starknet, and basically vice versa. And like I said earlier, this is way better because it gives you the chance to design or customize your own protocol. So you have the bridge available and you can decide what to send in the payload. So I was not able, I didn't really have like the chance to. I would have loved to show us an example of how you probably bridge should I say uh carry out cross L1 to L2 question um messaging with Ethereum. That's Ethereum to Starknet, right? Maybe we could just maybe I could go through the code if we still have time afterwards. I think I wrote one a few months back. So, but basically, like I said earlier, it gives you the opportunity to like design or customize your own protocol, as there is no assumption about the payload sent. Smart contracts can basically be customized or created on both sides to act upon the data that is sent by L2. So you can decide, okay, when I move ERS-20 tokens from Ethereum to Starknet or from Starknet to Ethereum, I want my smart contract to behave like this or behave like that upon basically receiving these assets. And assets can basically sit on any smart contract using the bridge. So in essence, there's really no locked liquidity anymore. So automatically Starknet has access to as much liquidity as is available on Ethereum, as you can basically move liquidity from Starknet to Ethereum and vice versa. Yeah, so like I said, the Start L1 integration, first of all, you have full control. You can send to an L1 or L2 contract different instructions for an arbitrary call. And basically, L1 liquidity is Starknet liquidity, which basically opens room to more liquidity on Starknet. So you can basically use this to directly access assets, ERS-20 token assets, NFT assets, etc. on L1 from like your applications. And I guess that would be it for this particular session. So we were also supposed to look into start with an introduction to security, basically look into common security vulnerabilities on Starknet, and probably you can get started as a security researcher. But we're going to continue that in our next class. So, but before we go, let's take the remaining time to basically answer questions. I don't know if you have questions. Can you probably just okay? Yeah, Temitope.
Yeah, thank you. Sorry, just now you mentioned that you about liquidity on L1 being available to L2, and you were saying we could access assets from the L1 from L2. Is that correct?
Yeah. So basically, you can access liquidity on like layer one and layer two.
Okay, so yeah, my question is how much of an access it is, because from your explanation you did mention that how would I put it, total finality for a block for total finality for a transaction is like 2 hours, because that's maybe the time it takes to for it to be finalized on Ethereum. So if you make, so I'm guessing the L1 to L2 messaging still falls under the same restrictions. So so that means you are limited. You have, if you send a message to L1 from L2, you don't have to wait for that. Do you have wait for that 2 hours for you to get a response back, or how does that work given the constraints around and being accepted on L1 and all that?
Yeah, so just like you said, Starknet, moving from Starknet to Ethereum, can be really super slow and very difficult to debug, right? Um, for moving from Ethereum to Starknet is very like super quick. So, but I don't think it goes against the concept of liquidity still being available. Yes, there are probably some limitations, such as the time required for bridging, and there are different ways people are trying to circumvent this. Right, you could look into the architecture of YAB, right, yet another bridge on Starknet. They came up with a means to circumvent this using Herodotus proofs, and yeah, so but like I said, it doesn't go against or negate the concept or the fact of the statement that okay, liquidity on Ethereum is actually available to Starknet or basically developers on Starknet. Okay, I can see the answer. Okay.
Okay, yes, I wanted to follow that up because I understand you do have access, but I just wanted to know the limitations, because what I had in mind was something like something like flash loans, for example. With this setup, it doesn't seem like it's possible to access the liquidity on L1 for that. In the case of like flash loans, to be particular, because of the way you have to return everything in one block.
Costing flash loans, I think that's that would be impossible at the moment. It has to probably be on Starknet, on Starknet, but costing flash loans doesn't sound like a possibility at the moment. Yeah.
Okay, understood.
Yeah, I don't know if anybody have any more questions.
Sorry, I was going to raise a plan before this. I asked the other time that will the slide be available after the class.
The slides.
Yeah, will it be available to go through maybe after
Yeah,
the
yeah, yeah,
whole
yeah,
session?
yeah. It will. It will. I don't know. David, is there like a shared Telegram group for the cohorts? Where can I share the slides?
Yeah, there's a Discord channel. I will also send that link to you for you to join. But yeah, you can send the slide to me and I'll share it on the Discord channel there. So, but I will also send an invite to you so you could join. And in case also further questions, which the participants will be having. They could also drop the questions on that channel on the Discord for that. Hope that is fine.
Yeah, that's fine. I don't think I'm on the Discord. Maybe can you just send
So
me?
you're not there at the moment. I will share the link. I will share an invite to you. I'll do
Oh,
that.
okay. All right.
Yeah, I'll do that. Okay. Do we have any other questions? Any other question? Okay. So I guess there is no more other questions. Let me just drop this here. I'll just drop it in. Okay, thank you, Mr. Darlington. This is an awesome session. Thank you so much for this. Okay, so I just want to give an update before we just call it there and give a quick comment and remark on the whole training. So this is Guild Audit. Guild Audit is a security, a Web3 security academy, or a Web3 security bootcamp based in Africa. Have different students from different part of the world. So we're really taking up this Starknet Security Cairo Bootcamp. So this is like 102. So we recently did 101, where it was just introduction to the security basics, right? That was like a month or 2 months ago. So we're also taking that same part to 102, but at the end of this 102, so we'll be going in depth a little bit more into the security aspect about it. The post bootcamp, right after this, like after the training, the idea also is we get to have like an alliance, right? So for students for participants who are eligible, right? So we'll be taking in, or we'll be taking in here your, we're assessing you guys and knowing who will be eligible for an alliance. So as a community also, we're trying to build a group of a group of people who are really good in Starknet security, also to help the community, to help the Starknet community itself. So what that entails is we get to do a lot of smart contract auditing for basic projects, right? Startup projects who are just building out. At the same time, we get to learn, and also as a team, we intend to also participate on Code for Arena. So, but this is really what will be happening post, right? The bootcamp itself. So I just wanted to share that knowledge also. So in moving forward, also we'll be having for this particular bootcamp also, we're having other instructors coming to also take different topics, right? Today we have Mr. Darlington taking up this for us. So in other subsequent class, we'll be having other instructors. Also, Mr. Darlington also have another class to take with us. We have the Discord channel for every communication. So please do drop every communication, ask your questions, communicate with your colleagues, right? I will really encourage you guys also. I will be dropping up some couple of number of resources. So I will really encourage you guys to delve into those resources from a security perspective and try to play and get your hands dirty, right, on those concepts, right? We also have I think vulnerable DeFi for Starknet. I don't know if any of you guys have seen that also, but I'll be sharing all of those resources for you guys to also get your hand dirty on those basic security concepts on Starknet. That will be the end of today's class. But I want to take some comments, questions, if there is any. Okay, I guess there is no question and no comment. Okay, thank you guys. See you guys tomorrow. Yeah, see you guys tomorrow. Same time.
Thank you. Bye.
Yeah, thank you.
Yeah.